Alright, so I wanted to make a video here since we missed some class time due to the snow. And so the questions I want to settle in this video, just a few here. These are the five big questions I'm going to try to settle today. Question number 1, how can we use coordinates to deal with linear independence and spanning? So that's the first thing we'll talk about. Then I want to talk about why is dimension well defined. In other words, why is it that if you have a vector space of finite dimension, there can just be one choice for that finite dimension? I actually have two rather different arguments for point number 2. I'll try to show you both. Question number 3, how do we modify a given set to make it into a basis? I already kind of tipped my hand there last class with the plus-minus theorem. That's kind of the answer to that. And then I want to share with you some fun facts about subspaces and their dimension, and then finally, if we have time, if the children give me peace, what about geometry? How can we view the solution set to AX equals to B as a linear manifold, and what does that even mean? All right, so let's get started. Question 1. All right. So, I'm going to find my cover sheet here. So question 1 here. Let's talk about that. Let me get Voltron and Donald out of the way here. There we go. So just to rehash here. Remember, beta is a basis, means it's an ordered set, right? A list, if you will. And it has to be two things: spanning, right? It generates V with finite linear combinations over F, and it's a linearly independent subset of V. All right. And furthermore, because we know that linear independence has the equating coefficients property, right? If we have A1V1 plus A2V2 plus equals B1V1 and so forth, well, that's true if and only if A1 matches B1, A2 equals B2, AN equals BN, right? So that means then that if you can find the coefficients with respect to the decomposition of a vector with respect to the basis, then we can define the coefficients as giving us the coordinate map, right? So the coordinate map is what? It is, if we have the vector x is equal to x1, v1, so forth and so on, then its coordinate vector is just the column vector x1 through xn. And today I'm going to introduce a new notation, function notation, phi sub beta. And this will be the coordinate map, just another notation for the same thing. All right, so like phi beta of x is x beta, but sometimes it's helpful to give a name to this as a function. The function takes inputs of abstract vectors, and it makes outputs of column vectors. All right. We say phi beta is the coordinate map on V over F with respect to the basis beta, or more simply, phi beta is just the beta coordinate map on V. Proposition 1. Proposition 1 here is that for the coordinate map so described, we have these two properties. We can pull constants out, and it's also additive. So like the coordinate vector of a sum is the sum of the coordinate vectors. The coordinate vector of a scalar multiple is a scalar multiple of the coordinate vector. But notice that the scalar multiplying here is happening in Fn. The scalar multiple here is happening in the abstract vector space. Likewise, this is an addition of abstract vectors. Over here you have an addition of coordinate vectors, column vectors in Fn. Taken collectively, this is known as the linearity of the coordinate map. All right. And then more generally, we can extrapolate for a set of k constants and k vectors in the vector space. We have this extended linearity. All right, we can pull out finite sums, constants, and addition. So let's look at the proof of that. Proof of linearity. So if x is built from the sum over xi vi, and y is built from the sum over yi vi, and c is in the field, well then I can look at z as cx plus y, put in my my sums, pull the c in, property of finite sums, rewrite this together as just one sum, and factor out the vi. So lo and behold, this shows me that the ith coordinate of z is exactly cxi plus yi. Therefore, the coordinate vector of z beta, or phi beta of z if you like, is exactly c1 x1 plus y1 plus cn xn yn. But then by the usual column vector arithmetic, we can pull those apart into c times the coordinate vector for x and then the coordinate vector for y. And there you have it. The coordinate map on z, which is of course cx plus y, is, I'll write it down here one more time. So just to recap, this is that phi beta of cx plus y equals that. All right. That was the outcome here of that calculation. Now that's very nice because then we can look at special cases. We put y equals to 1, y equals to 0 rather. That makes this go away because the coordinate vector of 0 is 0. And so that gives me 1. That I can pull a constant out, and then if I put c1 equal to 1, if I put c equal to 1, then that gives me the additive. It gives me part 2 of the proposition 1. And I'll leave the proof of 3 to you guys. You could use induction on k if you wanted to slog through the details there. That brings us to proposition 2. Proposition 2. Given a basis, all right, just like we've been talking about so far, for v, the coordinate map from v to fn is a bijection. What's bijection mean? That means that the mapping is a function. It's one-to-one and onto. So here's the proof. I'll pick a coordinate vector, a vector in fn. Let's call it c vector. Well, c vector is built from the sum over cj of ej, all right, where j equals 1 to n. And ej, of course, is the standard basis. Notice that if we use the same constants to build an abstract vector with the abstract basis, then that will map back to the c vector, right? Because if I write down w is equal to that, then by definition the coordinates of w are just c vector again, which shows you that, phi beta, right, phi beta of w is c, right? And that proves that the coordinate map is onto, because I took an arbitrary point in the codomain and I found a point in the domain w which maps to it. So that proves that the function, the coordinate map here is a surjection. Next up, I'll work on one-to-one rather, injectivity. So suppose the phi of beta of x is equal to phi beta of y. Let's call that star. Well, what that means is that there exists x1 through xn, yn through yn, such that if we build x like that and we build y like that, right, it must be that the coordinate vector of x is that, and the coordinate vector of y is that, and they have to be equal. But by definition of equality in column vectors, that means each one of these components has to separately be equal. In other words, xj is equal to yj for all j equals 1 through n. But that then says that x and y are equal. And so we've shown that the coordinate map is injective, and the proposition follows. So coordinate maps are bijections. That means that they're invertible. All right? So, proposition 3. Proposition 3 says that if we're given a vector space with basis beta and coordinate map phi beta going, as usual, point number 1, any linear dependence of vectors in V is in bijective correspondence to the same linear dependence amongst the coordinate vectors in Fn. And let me make good on this sentence with an equation. So what I'm saying is that if there exist vectors w1, wk, w1, w2, w3, all the way through wk, and constants over the field b1, b2 to wk, such that they have this linear dependence, right? They equal to, you can write them equal to 0 like so. That's true if and only if the corresponding coordinate vectors for these vectors and the same constants give you back 0. In other words, there's the same linear combination of the coordinate vectors of the wj's equal to 0. And of course, we know that the coordinate map is a bijection, so if I started with these, there's going to be a unique vector in the vector space that corresponds to each coordinate vector. So this arrow going both ways makes sense because of proposition 2. But anyway, just to recap here, a linear dependence in the vector space V uniquely corresponds to a linear dependence in the column vectors in Fn. And then once you know 1, it's easy to prove 2, which is that a subset S of the abstract vector space S1 data Sk is linearly independent if and only if the corresponding set of coordinate vectors, which would be phi beta of S, this is the image of S under the coordinate map phi beta. We should have talked about that in Math 200, right? The image of a set under a function, using that notation. Anyway, that's a set of column vectors, and that would be linearly independent in Fn. The proof of one implying 2, right? If you took a linear combination and set this equal to 0, it would force all the b's to be 0 for this guy, right? And likewise, that would force all these to be 0 for the corresponding linear combination over here, and vice versa. So you can easily see that. And likewise, if you had a linear dependence amongst these, it transfers to a linear dependence amongst these, and vice versa because of 1. So once we know 1, 2 follows pretty much immediately. So let's prove 1. So I have a proof in the notes, but I thought it would be good to sort of just work it out from scratch here, and so I do that. All right. So look at the coordinate map, and I'm going to point something out here, and this actually is important for future calculations, which is one way we can look at the coordinate map is by this soon-to-be boxed green equation, circled, so I'll circle it. This right here is such an important idea. We can view the coordinate map as a machine which changes the jth abstract vector to the jth standard basis vector. All right, that's what it's doing. It's going from the abstract vector space to the column vectors and just making this assignment. All right. Now, I'm not assuming this. I mean, here's the proof right down here. If I take Vj, I can write it as 0 times V1 plus da 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 plus 1 times Vj plus 0 times Vn. So you read off the coefficients, 0, da 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 da, 1, da da da, 0. That tells me that the coordinate vector of Vj with respect to beta is 0, da da da, 1, da da da, 0, where the 1 is in the jth spot, which is to say the green circled equation. See, because that is Ej. All right? And so if I have some Wj's, which I could expand in the basis Vi, right? So Wj, it's got to be the sum of Cji, Vi, where I ranges from 1 to n, right? I got to have these constants for each Wj because, you know, the W's are in the vector space, we're assuming. Here these B's are in the field. We'll write down the equation here just a second. So suppose I have 0 is equal to the sum of Bj Wj. All right, so I can take the Wj and I can expand it in the basis, right? So I take this Wj and I expand it across the basis with the appropriate coefficients, right? Okay, well, let me shut up. And then I rearrange the sum just for bookkeeping. I pull the sum over n first and put the Bj like that and the Cj. I mean, this step isn't absolutely essential to the proof. I just did it to clean things up a bit. Let's call that star. Then what I do is I take the coordinate map and take phi beta of 0 is equal to phi beta of star. Well, phi beta of 0 has to be 0 because the coordinate vector of 0 is 0. On the other hand, phi beta of star, using proposition 1, part 3, I can pull the sums out. I can pull the constants out, and I'm just left with phi beta of Vi. But you remember what phi beta of Vi is. We just argued that phi beta of Vi is Ei. All right? So this becomes sum over j equals 1 to k, sum over I equals 1 to n, Bj, Cj, I, Ei. Right? And then I just put the sum over n back where it should be, and go, wait a minute, well that's nothing more than the coordinate vector of Wj, right? It's the same coefficients as we built Wj with, except now standard basis instead of abstract basis. This is the coordinate vector of Wj. And there you have it. 0 is equal to the sum of j equals 1 to k, Bj, coordinate vector of Wj with respect to basis beta. And by the way, because of proposition 2, this calculation is reversible, right? So I suppose I really have carefully showed you this implies that, but the other direction is very similar. All right. So this calculation can be reversed. Thus 1 is true, and as I've mentioned, 2 immediately follows from 1. Now, this is the, you know, the in some sense, one of the fundamental ideas of abstract linear algebra is that we can take a problem with a problem in a finite dimensional abstract vector space, and we can trade that problem for a corresponding problem in column vectors. This is a very kind of sneaky idea. It's a very powerful idea, and this proposition 3 gives us the roadmap for how to do it, all right? Now, I'll continue with the theory in a second, but I think first we should look at an example which shows you how proposition 3 is put into practice. Let's do that. All right. So here it is. Again, proposition 3 allows us to exchange problems in abstract vector space V for corresponding problems for column vectors in Fn. All right. Let me show you. Come on, paper. You can do it. Separate. All right. So here's the problem. We would like to find possible linear dependence amongst these 4 2x2 matrices. All right. Now, if you just sit and look at these for a second, you should be able to see that if we take the first one and we add it to the second one, we get the fourth one. So there's at least one linear dependence, right? This plus this is that. The question is, are there any others? Is there like a hidden dependence amongst these 4? All right. I personally don't know until I calculate, all right? So what I do is I pick the usual basis for our 2x2, the lexicographic basis, as I talked to you guys about the other day. Sometimes we'll call that the standard basis for matrices. And so with respect to that standard basis, this has coordinates 1, 0, 0, 1. This has coordinates 2, 3, 3, 2, 1, 0, 0, minus 1, and then of course 3, 3, 3, 3. These are the coordinate vectors for S1, S2, S3, and S4 with respect to the basis beta. Now, that is a subset of R4. So I can decide the linear independence or dependence of this using the column correspondence property. So what do? I calculate. And so if we put those in the matrix, I call that matrix A, I row reduce that thing. After a little bit, I get to this one over here, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0. So apparently, the first 3 columns are linearly independent, and the fourth is the sum of the first 2, right? So by proposition 3, that means that S1, S2, and S3 are linearly independent in kind. So this is what the proposition does for us. It allows us to transfer a problem from abstract vector space to column vectors if we want. So S1, S2, S3 linearly independent because those correspond to pivots, whereas the fourth one is the sum of the first and the second column coordinate vectors, right? Therefore, by proposition 3, S4 is S1 plus S2. Now, we already saw that. I mentioned to that. You can just see it from the start, right? But what is perhaps, I say what is remarkable, right, is not that we have found S4 is S1 plus S2, but that there does not exist another linear dependence which were somehow hidden, right? The CCP, the column correspondence property, clarifies possible dependence because, you know, the reduced row echelon form, once we get to reduced row echelon form, then any kind of linear dependence, we're just going to be able to like just look at the matrix and see it, right? We shouldn't miss anything once we get to this point. And so that's reassuring, right? Now that we've done this, I have an add-on question which I won't solve, but I'll just state for you. So since we know that S1, S2, and S3 is linearly independent, right? Then you might wonder, what could we adjoin to those 3 2x2 matrices to get a basis for our 2x2, right? What fourth matrix, ABCD, could we adjoin to beta 1, 2, 3 to make beta S1, S2, S3, ABCD a basis? And how would you solve this? And what I mean is, what are all possible choices for ABCD that are going to work? You know, how would you do that? I'll let you think about it. But it should be fairly easy to see how you can use what I did up here and, you know, maybe get rid of this 3, 3, 3 and do something else. I'm going to shut up. I'll let you think about it. So that's, I've answered question number 1. It only took me 20 minutes. And now I will move on to question 2. Why is dimension well defined? All right. So there are a couple different approaches. Now one approach, as I said, a further theory of linear dependence, a tale of two maths. So the first story is based on Curtis linear algebra. And Curtis is a book I used a couple of years ago, and it's a rather sophisticated book, and it does have very, very nice presentation of certain things. Well, one of those things is this just series of theorems to get at what we're getting at here. He proves a lemma, 7.1, and the lemma is this: if A1 through AM is linearly dependent, and if A1 through AM minus 1 is linearly independent, then AM is a linear combination of the ones that preceded it. Now that seems like a really, really, like, well, okay, sure, but how do you actually prove that? Well, I think it takes me about 20 or 30 minutes to do it justice. If I recall correctly, this is not as easy to prove as you might think, and it requires an induction. And I have nothing against it. It's just I'm gonna focus our attention elsewhere. But if you'd like to read about it, Curtis Linear Algebra, Lemma 7.1. I think I got a copy of that sitting back here somewhere. Let's see if I can find it. Where'd you go? Where'd you go, Curtis? Ah, here you are. Yowzers. I'm back. I'm coming back. I'm back. This book is what I'm talking about. Charles W. Curtis, Linear Algebra, An Introductory Approach. So if you'd like to look at that, come talk to me in office hours or something. I'll let you look. But anyway, here's how Curtis does it. He says he proves lemma 7.1, all right? And then he uses that to prove theorem 6.62, which is that every finitely generated vector space has a basis, all right? And then, once he has that, he says, okay, well, if you have AM, a finitely generated vector space with generators A1 through AM, which is just to say that you've got a spanning set A1 through AM, he says, then a basis for V can be selected amongst the generators. In other words, a set of generators for a finitely generated vector space always contains a basis. So what he's saying is you can systematically remove these as needed until you take the spanning set and reduce it to become a linearly independent spanning set, and then bam, you got a basis. And then Curtis theorem 7.4, if you have a linearly independent set of vectors in a finitely generated vector space, and if B1 through BQ is not a basis of V, then there exist vectors BQ plus 1 BM in V such that B1 through BM forms a basis for V. Let's see here. All right, well, anyway, these, it's good to read these and try to meditate upon them, make sure that they make sense to you. But I'm not actually going to prove any of these. I just think this is the other kind of standard way to prove these things, and I thought I should at least spend a couple minutes mentioning this is sometimes the path people take. The path I will take, though, is more coordinate-based, and so what I'm about to argue here is that dimension is well defined, all right? And so to do that, what I do is I say, suppose you have a vector space over a field F, and suppose that there exists a basis B with B1 through Bn, a basis. Then the claim is this: any other basis for V also has n elements. In other words, any two finite linearly independent generating sets for a vector space V have the same number of elements. Well, this is sure comforting, because otherwise, It'd be awful embarrassing. You work with 3-dimensional coordinate vectors, and then your neighbor's got 2-dimensional coordinate vectors. How are you going to compare work, you know? That doesn't happen. I mean, the dimension is what it is. Let's see why. So here's the proof that dimension has to be the same, that you can't have. I mean, to prove the dimension's the same from to use the theorems in Curtis, there's other arguments, but I like this argument here. So let's look at it. Suppose you got two bases, B and F. All right. Well, that means that both of these are linearly independent and both of these are spanning for the whole vector space, right? So in particular, BK must be in the span of F, right? Because F is a basis. So that means that there have to exist constants CIK, such that BK is C1K F1 plus C2K F2 plus CPK FP for some constants C1K, C2K, CPK in the field, all right? And similarly, we have to be able to take each vector in the basis, the F basis, and expand it in terms of the B basis with different coefficients, possibly 1J, 2J, NJ, right? Again, these are in the field. And the thing is, if we take these two, and if I take take this one, and then substitute in that one into here, into there, then we get this down here. So substituting the one expansion into the other gives me this. Oh my goodness. So Fj is equal to d1j times that linear combination of f's, d2j times that linear combination of f's, and so forth. And then you can collect things together, right? You've got like an F1 and F1 and F1 all the way down. So, and you got coefficients like d1j c11, d2j c12, dnj c1n, F1, and then whatever goes with F2, whatever goes with FP. And the thing is, that is equal to this, but remember the F's are linearly independent, so we can equate coefficients. So that means that all of these are 0 except for the j'th one. And I write it out, you know, kind of one at a time down here. Right? So like d11 c11 plus d12 c12 plus dn1 c1n is 1 for j equal to 1. And then still in the j equals 1 case, but for F2 we get that. Still, you know, and so forth. And if you collect your collect it all together, what you got is that the Kronecker delta Q1 is equal to CQ1 D11 plus CQ2 D12 plus CQN D1N. And if you look at that, what we're really doing is, well, this is a matrix, right? We can look at the constant C and the constants D as forming matrices, and what you're really looking at there is something like, what is this? This is the sum. How's it go? 1, 1, 2, 2, all the way up to n, right? So let's say K, I use K elsewhere? No, K has not been used here, has it? Only as a variable, so it should be okay. K equals 1 to n of C QK D K1, right? And so that would also be like the matrix C times the matrix. Oh, I don't need these, right? It'd be matrix C times matrix D, the Q1th component of it, right? So you look at this, all right, sort through the notation, and what you got is something kind of pretty. You can do it for arbitrary j, and you'll find that delta qj rather is equal to this, which of course is the sum over C qk d kj, k equals 1 to n, which we recognize as the matrix C times the matrix D, the qjth component of it, right? Or I've used capital C and capital D for the matrices down here, right? But you see what you got. You got C times D is IP. That makes sense because we're doing, this is a P by N times an n by p by n. Oh man, I think one of these is supposed to be oh, I messed up the notation. Just a second, folks. Go back to the start here. N and P. Oh, okay, yeah, P and N. Oh, never mind me. Ignore me. So P by N times N by P, right? So this is a P by P. All right, as I said, it's equal to the P by P identity matrix. But there's nothing really stopping you from making the exact same argument juxtaposing the roles of C and D, which would give you that D times C, which would be a N by P times a P by N, right? That would be an N by N matrix. It gives you DC is equal to IN. But the trace, the trace of an identity matrix, like what's the trace of 2 by 2? 1, 0, 0, 1. It's 1 plus 1, it's 2. So like the trace of IP is P, the trace of IN is N. And also in your homework you will prove that the trace of CD is the trace, well you would prove the trace of AB is equal to the trace of BA. And there you have it. That does it. We've just proved that the dimension is well defined because P is equal to N. We can, if we have a basis with a linearly independent spanning set with N things, and we have another linearly independent spanning set, it must also have N things. It's not up for grabs. So that shows you that dimension is well defined. Next up, of course, well, there's a few theorems in here I should just kind of mention. I think these are, this one's kind of weighty. Proposition 666. Oh no. Okay, well, probably shouldn't even cover this one, right? But sorry, I'm an idiot. But so this one here, what does it say? If V is a vector space with dimension n, all right, and if S is a set with more than n vectors, then S is linearly dependent. If S is a set with less than n vectors, then S does not generate V. Right? That means that the span of S is not equal to V. Okay, that's what that means. Does not generate V. This is easily proved with proposition 3 in what we know about vectors, column vectors, right? If you have column vectors, if you have more than n column vectors in Fn, they're linearly dependent, right? And if you have less than n column vectors in Fn, it doesn't generate all of Fn. And then when you feed that through proposition 3 that we proved today, that will prove 1 and 2 here. Okay? And that's more or less what I'm doing in here, which you can skip if you want to just focus your attention on the proposition that I wrote out today. That's fine with me. You don't have to read this part of the notes if you don't want to. Don't take me out of context here. I'm not saying that that proposition doesn't matter. I'm just saying that the way I proved it in the notes, we have supplanted that with an explicit calculation that I wrote out earlier in this lecture, right? With the C's and the B's. Here we go. Proposition 6.67. Suppose V is a vector space with dimension n, and W is a subspace of V. Then there exists a basis W, a basis for W, and the dimension of W is less than or equal to n. So again, the fact that the dimension W has to be less than or equal to n would be easy to prove from proposition 3. Let's see here, what's my proof say? If W is 0, the 0 subspace, then the proposition is true because we can pick the empty set as a basis, right? Suppose that the set is non-zero and let S be a finite subset of W. We can apply proposition 666 to modify S to a basis beta W for beta by possibly deleting or adjoining vectors from W. Yeah, I think, well, I mean, yes, but I think maybe honestly, I mean, okay, it's not crazy, but I really think it makes more sense to use this one here, because the way we can modify a given set to a basis is to use this this so-called plus-minus theorem down here. All right, let's again look at, I mean, I talked about this in class already, but let's talk about it again a little bit. V a vector space, suppose S is a finite non-empty set of vectors in V. S is linearly independent with non-zero vector V. Not in the span of S, then S union V is a linearly independent set. So this tells us how to build bigger linearly independent sets from a given one. You start with linearly independent set V S. You can make a bigger linearly independent set S union V as long as you pick V outside the span. All right. That's part of the reason I've asked you guys questions about when are vectors in or out of the span. I'm trying to prepare you to give you the skill set you need to start building bases. All right. And then part 2 here is, if we find one vector is a linear combination of others, then we can remove it and not change the span. So this one gives me a way of adding vectors to make the potential basis bigger. This part 2 gives me a roadmap for removing vectors from S to make it linearly independent. Both of these roads lead us to change S into a basis, let's say, for V. And the same logic can be applied to a subspace as the whole space, all right? Anyway, enough about that. We'll move on here. This one's important. And it's important to make sure you understand the context in which this is stated, all right? Because the context is everything. Okay? Let V be an n-dimensional vector space. So somehow, at the start of everything, we know, without a doubt, that V is an n-dimensional vector space, all right? Given that backdrop, let S be a set of n vectors in V. The following are equivalent. S is a basis of V. S is linearly independent, and the span of S is V. So this is very nice, but you got to remember the context is V being an n-dimensional vector space. So for example, where would we know V is an n-dimensional vector space? So like, for example, we could have something like V equals to P2R, right? That's built from the span of 1x and x squared. Oh, thank you, Benjamin. Yeah. You got my phone for me. That's very nice. Yeah, thanks. Thanks a lot, man. So P2 is the span of 1x and x squared. That means the dimension of V is 3. All right? So if we look at S equal to, 3 polynomials, let's say 1 plus x, 1 minus x, and 2, right? Then the question of whether or not S is a basis, S is linearly independent, whether the span of S gets all of V, these questions are inextricably connected. If I settle any one of these, I've settled the other two. I look at these 3 vectors, I notice that 1 plus x, but if I take the first and the first 2, right, you notice that 1 plus x plus 1 minus x is equal to 2. That shows that S is not linearly independent. So I've ruled out 2, which means I also know what? Okay, it's disqualified from being a basis. It's not a basis for V. And you know what else? This is not going to span P2. There's something missing. And you can see what's missing. It's the quadratic, right? But this is an important proposition. Perhaps we'll look at the proof of it someday. Not at the moment. This is Theorem 6.61. So, this part of the notes, it's not logically minimal, all right? Like, there's some overlap here. There's probably a lot of overlap. And it could probably be, I probably could take all of these theorems and replace them with about 40% of what's here. So there's some duplication, and I hope that's not too offensive. Well, if it is, you're free to rewrite my notes and send them back to me in their logically minimal form. I sometimes wish I lived in a world where I was just teaching this course and I could just fix everything, but, life. So, theorem 6.6.11, let S be a subset of a finite dimensional vector space V if the span of S is V, but S is not a basis, then S contains a basis, which can be constructed by removing redundant vectors. This was one of those results which was in the thing it was one of Curtis's theorems as well. And if S is linearly independent and the span of S is not equal to V, then S can be extended to a basis for V by adjoining vectors outside span S. What I mean is, isn't this just the plus-minus theorem? It's very close. It's not exactly the plus-minus theorem, but it's awful close. But there it is, and the proof down here might be worth looking at. Let's actually do that. So the proof of 1. If the span of S is V, but S is not a basis, that means what? That means that S is linearly dependent, right? Because if S was linearly independent, then it would be a basis, right? Because it's already a generating set for V. Okay, since S is linearly dependent, that means that we can write some vector V in S as a linear combination of other vectors in S. And furthermore, by proposition 666, the span of S, man, I think that's a typo, guys. I think my label has gotten unlabeled. That is not supposed to be that is not supposed to be 6. I do not think that's supposed to be. Yeah, that is not supposed to be 666. That is, you're like, well, that's good. That is supposed to be 668. That is 668, folks. 668. All right, because it's this theorem that I'm referring to, okay? 668. All right, moving along. Note to self, must fix. All right. So we can remove V, which is a linear combination of other vectors in S, and not change the span. Now, if S with V removed is linearly independent, bingo, we got a basis, so we're done. But otherwise, it's linearly dependent, and we can remove another vector. And we can continue until the resulting set is linearly independent. We know this happens when there are just dimension of V vectors in the set, right? So this is not an endless loop. Notice the context here. Finite dimensional vector space V, all right? And I guess, to be fair, I'm assuming that S is a finite set. That should be stated, really. Finite set. Because otherwise, this could take a lot more loops if we want to be so loopy. Now, part two here. If S is linearly independent, but the span of S is not equal to V, that means that there's some V that's in the vector space, but not in the span. And so proposition, hey, look, I got that one. 6.68 shows that S union V is linearly independent. And again, so if after adjoining V we get the whole vector space, that means that S adjoined with V, unioned with V there, is a basis. Otherwise, there's still some vector outside, and then we repeat. And this argument so forth until we get up to the dimension of n number of vectors, which span V. And again, we know this is not an endless loop because V is finite dimensional. And once the set is linearly independent and contains dimension V vectors, it must be a basis. All right? So, I guess one question I've kind of been skirting is, given a vector space, why is there a basis, right? And, well, that's a tough question in general. The vector space could be, but you can prove this in general. If the vector space is infinite dimensional, you need to appeal to something called Zorn's lemma. And I recently went through the proof of this in the topology special topics course I'm doing right now. So you can look over there and see it if you want. It's kind of tough. But of course, for finite dimensions, basically we have the theorem: if you have a finite set of vectors which spans the space, that means it's finite dimensional. If there does not exist a finite set of vectors which spans the space, then it's an infinite dimensional vector space. Now, we talked about subspace theorems before. I don't think I have much to add here at the moment. I think I already told you guys about the rank nullity theorem for a matrix, didn't I? Maybe I did, maybe I didn't. The rank of A is equal to the dimension of the column space of A. The nullity of a matrix A is the dimension of the null space. But if you think about it, the dimension of the column space is the number of pivot columns. The dimension of the null space is the number of non-pivot columns. So if you add these together, how many do you get? You get the number of columns, and that's the rank nullity theorem. So the n is equal to the rank of A plus the nullity of A. So an important thing to know about, because if I give you partial information about, the rank or the nullity and the size of the matrix, well, you can figure out whatever piece is missing. I mean, here's three things: n, rank A, rank nullity of A. If I give you two of these things, you can figure out the other one, right? Next up, we just have a few small comments. One of the things I've asked you to prove in the homework is that if we have two subspaces, the intersection is again a subspace. Use the subspace test theorem to prove that. It shouldn't be bad. Another thing you can do is union of two subspaces does not usually form a subspace, right? I mean, just think about like union of the x and y, x-axis, y-axis. Both are subspaces of R2, but their union, just the coordinate axis, is of course not a vector space. The smallest subspace of a vector space which contains the union is this sum of u and w, u plus w. It's just the set of all x plus y, x be taken from u, y taken from w. This is actually a subspace. You can prove that. And so, theorem, if V is a vector space with subspaces u and w, then u plus w is also a subspace of V, and no smaller subspace contains the union. Again, I believe that is one of your homeworks, and it's not too bad, that one. This is sometimes nice to know. If V is a finite dimensional vector space with a subspace W, then the dimension of W is less than or equal to the dimension of V. Notice that this statement is very different than the one below it. This is our notation for saying W is a subset of V, which is a vector space in its own right with respect to the natural operations of V. The statement dimension of W less than or equal to the dimension of V is a statement about real numbers, in particular the number of things it takes to make a linearly independent spanning set for W versus that for V. And fun fact, you only get equality when W is equal to V. So the proof is here, and again it involves the same bag of tricks in terms of looking at a basis or a linearly independent set and extending it. The type of argument that's given right here actually becomes more important in applications of linear algebra past this course. Let's see here. I'm almost out of time, I think, so let me try to wrap this up here. Uh-oh. This is not an easy theorem to prove. I mean, it took me a while to sort through the proof here, and if I do it in class, it takes me a whole period. Or at least a half hour, I don't know. The dimension of u plus w is the dimension of u plus the dimension of w minus the dimension of the intersection. So it's the proof is kind of involved, but you know, there you go. That's the relation between the dimensions of the sum and the subspaces and their intersection. All right. So this is at times very useful. The more you know, right? Now, so last is the general theory of linear systems, and in this section, I try to look at the problem of ax equals to b again in a fresh new light and see what we can say about it. So what can we say? Well, first of all, proposition 6.81 says that if you have two solutions to m equations and m unknowns, then any linear combination is also a solution. So, I mean, in other words, proposition 6.8.1 really says that the null space of A is a subspace, right? This is essentially just a different way of saying null space of A is a subspace of Fn. Oh, look, I said that right there. Okay. Let's see here. What's proposition 6.82 say? We have vectors. We put them together. AV equals to 0 if and only if AVI. So I'm taking a bunch of homogeneous problems and putting them together as one big matrix homogeneous problem. This kind of thinking is important in differential equations. This is a solution matrix. V is a solution matrix, means that every column in V is separately a solution to the corresponding vector problem. I'm not sure how much this matters to us at the moment, but there it is. Ooh, yay! The plow. This is actually a pretty good place for me to stop today. So what, you know, we've talked about subspaces, we've talked about vector spaces. I've introduced the concept of a column space. So what is that? How does that tie back into you know, our solving systems of equations? Well, here it is. System of equations ax equals to b is consistent, all right, if and only if b is in the column space of A. So it's just this, ax equals to b means that this is equal to b, right? But if you repackage that, it's really just nothing more than the sum of columns of A equals to b. That's a linear combination of columns of A being equal to b, which is to say that b is in the column space of A. All these calculations are reversible, so there you have it. So this is something that you definitely need to know. What does it mean for the column space of A? If the inhomogeneous term is in the column space, then we can solve the system. If it's not, then we're out of luck, right? And then finally, drawing things back together here, if we have a consistent system, in other words, if B is in the column space of A, then we can write our solution as a homogeneous plus a particular. The homogeneous, of course, breaks down to C1 V1 plus C2 V2 plus C nu V nu. Here nu is the nullity of A. It's the dimension of the null space, the number of non-pivot columns. And the xh is the homogeneous solution because A times xh is 0. The vj, j equals 1 through nu, these are bases for the null space. That's why the nullity is nu. And of course, p is the so-called particular solution, that terminology being very popular in differential equations. And so anyway, the general solution is a sum of the homogeneous and the particular solution, also true for linear systems. And I have an example, but I think I'm out of time. Next up, I mention, just to recap, ax equals to b is consistent means that the general solution has as many parameters as in the dimension of the null space of A, which I called nu, the nullity of A, in the previous page. Now, in Math 334, we solve kind of a similar problem. We solve L of, something like L of y equals to g, where L is a smooth differential operator and g is a forcing term, which is actually a function. Technically speaking, this equation's happening in infinite dimensional context, but something special happens with the analysis and the solution space ends up being finite dimensional. And because of that, we're allowed to bring to bear tools of finite dimensional linear algebra to solve the nth order problem. This is a rare and precious and wonderful thing that happens in the theory of the Wronskian and all that is tied into this story. And we can talk more about that some other day. I mentioned it in passing here. Last up, linear manifolds. What's a linear manifold? I may not have even assigned you a problem about this. I can't remember. I'll have to look. But just to give you a whirlwind tour of this idea, V is a vector space, W is a subspace, P plus W is a linear manifold of V. So basically something like this could be a linear manifold, or in 3 dimensions you could have things which aren't going through the origin, right? So this would be something like P plus W, because we move away from the origin by P and then we have the whole subspace W. Sometimes these are called affine translates, because it's a translate of a subspace by P. Anyway, this is a linear manifold, and the vectors in W are tangent to P plus W, and W we also call the directing space. Linear manifold is not usually a subspace. However, if W is a subspace of V and P is in W, then P plus W is W again. Anyway, so here's the proposition. If AX equals B denotes a system of M equations and N unknowns, and XP is the particular solution of the solution set, well then the solution set is a linear manifold of the form the particular solution plus the null space of A. So the solution set to a system of linear equations is a linear manifold. It basically looks like a plane which is translated off the origin, generally speaking. Now, the inverse question, does every linear manifold in Fn appear as the solution set for a system of linear equations? I have at times found this question to be somewhat challenging. And it just depends on how tired I am or how I get asked the question. But here's an example of how to work backwards from a linear manifold. I look at this particular subspace of 2 by 2 matrices, and my base point 1, 2, 3, 4. So like this gives me a typical point in this linear manifold. That a typical point would look like, how's it go? If A is in P plus W, then it has x2 plus x3 minus x1 plus x4 equals to that. And anyway, so I sort through it and I eliminate S and T, and that brings me back to just a system of equations. x4 equals to 5, x3 equals to minus 1, and so that original linear manifold is the solution set to this x1, let's see here, x1 minus 1 equal to that, x2 plus x3 minus x2 equal to that, x4 equal to 5, x3 equal to minus 1, I gather. Anyway, if I had any sense, I didn't ask you one of those. it tends to... anyway. But anyway, here it is. If V is a finite dimensional vector space, W is a subspace, P is in V, then P plus W is the solution set for a linear system of equations. And what this proof is basically just a formal mockery of what I just did in the previous example, showing that I can take this kind of abstract span and translation and convert it back to a system of equations, and view this as the solution set to a particular set of linear equations in the correct way. Anyway, this goes back to the question of Calculus 3 if you've had it. Do you want to look at things as like a parameterized set, or do you want to look at as an implicitly defined set, right? Is it Do we define our surface as a parameterized surface, or do we define it as a level surface, right? What's the right viewpoint? In my view, P plus W is sort of the parametric viewpoint.